Hello everyone, my name is Chen. I'm a third-year PhD student at Brown, and today I'll be presenting our paper on how we leverage the traditional notion of retrieval axioms and combine it with the new and upcoming research we're seeing in the broader NLP field of mechanistic interpretability to reverse engineer relevance computation. And this is work done with my co-author Jack Merullo, who's not here today, and my supervisor Carsten Eickhoff. So, as we all know, AI has become a large part of our lives. I don't think I have to tell you that based off of the number of LLM sessions we have this year at SIGIR. But I also want to remind everyone where cases AI has failed, and they have failed in disastrous ways. I'll just put it at that. So there's a serious need for understanding how these models work so that we can identify when they might fail and adjust accordingly. So what does explainability then look like for retrieval? Let's consider our classic ranking scenario where we have an input query and we want a model to return a ranked list of documents in order of relevance. So the question here then becomes, how do ranking models determine relevance? Well, even to us as humans, the notion of relevance isn't exactly largely defined, but we do have an intuition on these criteria, and for that we can turn to the traditional notion of axioms. And for those of us who are not familiar with axioms, these are formal constraints that should be fulfilled by a good ranking model that researchers have defined. An example of one of these is term frequency, and a term frequency axiom states that documents that have more occurrences of query terms should have higher ranking scores. So now that we have these concepts of relevance, the question then becomes, do neural models learn these concepts? One way we could go about doing this is a method called probing, which you take your trained retrieval model and you train a lightweight classifier on top of it in order to measure how well representations can perform a task. And while these methods can test whether models learn these concepts, these results are correlational, and it's unclear whether or not these concepts are used at inference time. So how can we gain a causal understanding of neural retrieval models? For this, we propose turning to mechanistic interpretability methods, which is gaining traction in the broader field of NLP. And the methods here aim to reverse engineer a neural network to understand and localize its internal decision-making mechanisms. And this has been used with success to investigate gender bias in large language models, locate and edit facts in GPT, and also been used to identify computational graphs or circuits in natural language inference tasks such as indirect object identification. And a key outcome of all of this research is the ability to construct these computational graphs or circuits in which research has found that model behavior is highly modularized to the extent of even just a couple attention heads in a transformer-based model. And then we can analyze these components to classify their behavior. And this is just an example of what a circuit can look like. And as you can see, there's just several modules here in which a model is able to perform the natural language inference task of indirect object identification. So in our perspectives paper, we take the more traditional side of IR, stemming from retrieval axioms, and leverage the more recent and quickly growing work of mechanistic interpretability to propose this hypothesis testing framework for localizing relevance in transformer-based retrieval models. And overall, this will allow us to gain a more granular and nuanced understanding of how retrieval models operate. So taking a step back and going over how this behavior is modularized, this is an example of the traditional transformer diagram, which implies this almost linear flow of information through the model. But if you recall, transformer blocks utilize residual connections, which adds the output of the attention blocker MLP to its input. So because of this, we can re-visualize the flow of information through the model in a different way. And we can say that transformers read and write information to a common residual stream. And what this essentially implies is that upstream components can communicate with downstream components, and they can send important information along this residual stream. So, how do we determine which components are important players in this information exchange? We can turn to activation patching, which is a causal intervention method used on input pairs to identify these specific network components that are responsible for this difference in behavior. In our paper, we use this to isolate the term frequency axiom that I mentioned before that says that documents that have more occurrences of query terms should be ranked higher. So what we can do is we can construct a pair of documents in accordance to this axiom in order to examine the difference in ranking behavior. So an example of this is we take our query, for example, the average snowfall in New York City, a corresponding document, and we randomly select a query term, create a copy of our original document, and perturb it in a way such that we append the selected query term to the end. So now we have these two sets of documents in which one has an additional instance of a query term than the other, and the expectation is that this perturbed document has a higher ranking score than the other because it has more instances of the query term. So then the question becomes, what components cause this difference in ranking score? And here in our paper, we introduce activation patching for information retrieval. So we take our input pairs, or input document pairs, our baseline document, we'll call the original one, and the perturbed document, which has an additional query term. And we'll do a couple forward passes in order to isolate behavior. So we do a forward pass on our original document and record the score. And then we do our second forward pass on our perturbed document, also recording the score, but this time caching the activations. And this is because on a third run, which we'll call our patched run, we start the forward pass on the original baseline document and iteratively cache activations from our second run, and then let the model update the rest of the components downstream, and we try to see how that affects the overall ranking score. So how do we know if a component that we patched in is important? Well, if you recall, we start off our patched document run on the original baseline document. So if a component is important when we patch it in, we want to observe how much does this intervention increase the ranking score. So we perform all of our experiments on a Dilbert-based retrieval model, just has to be. There are 6 layers in this model and 12 attention heads per block. And just to note the way that the ranking score is calculated here, queries and documents are encoded separately, and the ranking score is calculated as a dot product of the CLS tokens. To create all of the minimal document pairs we use for our experiments, we utilize MS-Marco and select 100 queries from the data set. And for each query, we retrieve the top 100 relevant documents and create the perturbations. So our results can show that patching directly into the residual stream can reveal key layers and tokens that are important for relevance calculation. So here in the blue, an intervention, the blue represents that an intervention or patch has increased the score. On the x-axis are the different types of tokens. We have the CLS token, we have the duplicate query terms, and we have layers 0 through 5, so the 6 different layers. The end of the model is at the top in this diagram. And what we could find is that in the last 2 layers, the CLS token is the most important. And this makes sense because this is how the ranking score is calculated. What's interesting to find is that in the early and middle layers, the duplicated query terms, the ones that we injected and have multiple instances in the document, are the most important. So the question is, okay, what's going on in these early and middle layers? Well, what we can do is we can patch on individual attention heads in order to figure out what's going on here. And what this diagram is showing is, again, the blue indicates important components of the model. We have 12 different attention heads across the 6 different layers. This diagram is flipped, so the beginning of the model is at the top and the model is at the bottom. But the takeaway from this is that the term frequency calculation is highly localized to just these 4 attention heads across the first 4 layers of the model. So using these insights, we can begin to build a computational graph for relevance calculation, which is essentially just a way of what the model is doing to calculate relevance. So given our input documents, we looked at the attention scores for these 4 different attention heads, and we found that the heads in the first 2 layers primarily attend to these duplicate instances of query terms. And so we call these heads duplicate token heads. The heads in the next 2 layers, when we looked at the attention scores, we found that these heads don't attend to any single token, but they still strongly impact the ranking score when they're patched in. So we hypothesized that the upstream duplicate token heads are sending important information to these downstream relevance composition heads, and that these relevance composition heads use this signal in order to determine the final ranking score. So these experiments are only a starting point for understanding how retrieval models work. We have more details in the paper, but what I really want to highlight is what these experiments mean for the future of interpretability research in IR. So in this paper, we utilize activation patching to show the potential of these methods, but there are other things we can investigate, such as the direct component interactions. So how do components interact, and what exact information do they send and receive? Some things we could possibly do are investigate the key query value vectors in the attention heads, and that'll tell us more specific functions and about this behavior. We can also look at the generalizability of these relevance axioms. To what extent do other models encode IR axioms? How does relevance computation differ across different domains and contexts? We could also use this method to mitigate adversarial attacks. So like the previous presentation, as you saw, you can have certain trigger words that when you inject them into a document, adversely affect the ranking. So potentially here, could we localize the components that are involved in this and build safeguards against those adversarial attacks? And finally, I think this is all leading up to the idea of model editing, and I think this is a really interesting and exciting research space. So the question is here, if we can localize the components that are responsible for relevance, can we intervene on these components to improve model performance? Or we could also intervene on them to mitigate undesirable behavior, such as gender bias, which is something that I'm currently looking into. And overall, with these mechanistic interpretability methods, we can gain a much more granular and nuanced understanding of how relevance is computed in retrieval models, leading to ultimately more controllable systems. If anyone's interested in getting started with this, please check out our paper.